Let's have a further look at linear equations. We'll have a look at systems of equations where we seem to have an infinite number of solutions. Solutions involving a parameter. Let's consider a system of equations here. 3 equations involving r, s, and t. And we can start off by writing this system of equations in the augmented matrix form here. So the augmented matrix, it includes the coefficients. What it doesn't include is the variable names r, s, and t. Let's see how we would process this augmented matrix using row operations. Firstly, we would like zeros in the 2 positions here. And we can get a 0 here by taking row 2 and subtracting 3 row 1. We can get a 0 here by taking our row 3 and adding row 1. So the first row remains unchanged. We have 3 minus 3 times 1. We have minus 1 minus 3 times 4. We have 2 minus 3 times minus 2. 2 plus 6 gives us 8. We have 3 minus 3 times 2. That's minus 3. And then for our bottom row, we add on the top row. So minus 1 plus 1, that's 0. 9 plus 4 is 13. Minus 6 plus minus 2, minus 8. And 1 plus 2 is 3. So we have zeros in the 2 positions here. We'd like to get a 0 here without destroying the 0 here. So what we can do, we can take our row 3 and we can add on row 2. So the first 2 rows remain the same. And then the third row, 0 plus 0. 13 plus minus 13, that's our 0 here. Minus 8 plus 8, well, we seem also to have a 0 here. 3 plus minus 3, that's 0. And we do note that every entry in the bottom row is now 0. So when we look at what this now represents in terms of our equations, r plus 4s minus 2t is 2, one of our original equations. Minus 13s plus 8t is minus 3. The third equation simply says that 0 is equal to 0. There's no information here. We can proceed towards a solution because actually this 0 equals 0, the lack of information, also represents the lack of a restriction there. And what we can actually do is set one of our variables, say t in this case, equal to a parameter. Let's say t is equal to lambda. Third equation is satisfied. Second equation, minus 13s plus 8 lambda is minus 3. So we end up here, s is 8 lambda plus 3 all over 13. And then we can make use of the first equation here. We can make use of the first equation. R plus 4s will be 32 lambda plus 12 over 13. Minus 2 lambda is equal to 2. Our first equation now tells us that r is equal to 14 minus 6 lambda divided by 13. So we do have r, s, and t all in terms of lambda. Pick any lambda, r, s, and t will satisfy the equation. We can see some here. Lambda is 0, lambda is 1. We have r, s, and t. R and s in terms of 13ths here. But we can pick other values of lambda that give r, s, and t as integers. We have an infinite number of solutions, including an infinite number of solutions where they're all integers. We should note that the determinant of the original matrix of coefficients, it turns out, is 0. We have a singular matrix here, so working things out from the inverse matrix would not, in this case, have yielded result. So if you're attempting to solve a system of m equations in m variables, and you end up with the mth row all being 0, then you will be able to express your solutions, an infinite number of solutions, in terms of a parameter. If the second last row is also 0, you will be able to use 2 parameters. Now this situation, where you have your expressions in terms of a parameter, you have the 3 planes, each representing a single equation, intersecting along a particular line. So the line here, we can see that it's more obviously the intersection between the blue and the orange planes. It turns out that the green plane also lies as a part lying down the line here. We can look at the intersection of the 3 planes from various different angles here. Yes, we can see blue and orange here, but we can see we have the intersection between the blue and the green planes here. Green and orange, they do all lie along the same line. We can try and align it so that we are looking down all 3 planes here. So we can see there's a line moving away from us here where all 3 planes intersect. We're now asked to solve a system of 3 equations in x, y, and z. Use row operations to find all of the solutions of the following system of equations. Here's our system of equations. We can write down the augmented matrix, so we take the coefficients from the equations 1, 2, 1, 11, minus 2, 3, 5, minus 1, minus 3, 7, 10, 6. That's our augmented matrix. We would like zeros in the 2 positions here. So we'll take row 2 and we'll add on twice row 1. We'll take row 3 and we'll add on 3 times row 1. And then row 1 will stay as it is. So that's row 1. For row 2, minus 2 plus 2, 3 plus 2 times 2, 3 plus 4, that's 7. 5 plus 2 times 1, 5 plus 2, that's 7. Minus 1 plus 2 times 11, minus 1 plus 22, that gives us 21. Row 3 plus 3 row 1, minus 3 plus 3, 7 plus 3 times 2, 7 plus 6, 13, 10 plus 3 times 1, 10 plus 3, 13, and then 6 plus 3 times 11, 6 plus 33, 39. So we've got zeros in the 2 positions here. We'd also like a 0 here to make the system upper triangular. So what we'll do, we'll take 7 of row 3 minus 13 of row 2. And we'll keep the first 2 rows as they are. We'll have 0 here. 7 times 13 minus 13 times 7. And again, 7 times 13 minus 13 times 7. 7 times 39 minus 13 times 21. That's 273 minus 273. It gives us 0. We note now our bottom line is all zeros, so we will have an infinite number of solutions. We could set z equal to a parameter. We'll use z is equal to lambda. Our second equation, 7y plus 7z, which will be 7 lambda, is equal to 21. So we have that y plus lambda is equal to 3, or alternatively, y is equal to 3 minus lambda. So if z is lambda, y is 3 minus lambda. Let's see what the first equation now gives us. X plus 2y, that's 2 times 3 minus lambda, plus z, which is equal to lambda, that is equal to 11. Or x plus 6 minus 2 lambda plus lambda is equal to 11. X minus lambda is equal to 11 minus 6, which is 5. So x will be equal to lambda plus 5. So we can now say that for any lambda, we'll have that x is equal to lambda plus 5, y is equal to 3 minus lambda, z is equal to lambda. For any value of lambda, what we'll get here will be a solution to all of the equations. We can check. For a couple of specific values of lambda, if we have lambda is equal to 0, we'll have that x is equal to 5, y is equal to 3, z is equal to 0. This is one solution to all three equations. For lambda equals 1, we'll have x is equal to 6, y is equal to 2, z is equal to 1. We can put in any value of lambda, and we will get a combination of x, y, and z, which satisfy the equations. For example, let's run a check. For lambda is equal to 1, where we have, of course, x equals 6, y equals 2, z is equal to 1. X plus 2y plus z will give us 6 plus 4 plus 1, that is 11. as mentioned in the equation. We have minus 2x plus 3y plus 5z. We'll have here minus 12 plus 6 plus 5 times 1. That's minus 1. Again, as mentioned in the equation. And then we have minus 3x plus 7y plus 10z. Well, that's going to be minus 18 plus 7 times 2 plus 10 times 1, 24 minus 18, that is 6, also agreeing with the original equation. We've checked the values for lambda is equal to 1, but they would check out for any value of lambda. So where the coefficients on your left-hand side form a determinant that is 0, one possibility is that you will have an infinite number of solutions and you can express them as here in terms of a parameter.